A hearty welcome to one and all. I am Rohini Batwal from Gokule Education Society's JDC Bitco English Medium High School with 8th standard science subject, and my topic is sound. Students, can you recall how is sound produced? We have learned that students, sound can be generated from a vibrating object. With an example of tuning fork, we will now learn about how a sound is produced due to such vibration. A photograph of tuning fork is shown in figure 15.1. A tuning fork is made of two prongs and a stem. Keeping the stem steady, if the prongs are stuck, they start vibrating. Students, figure 15.2 shows a stationary tuning fork. To show the state of air around the tuning fork, vertical lines are used. Here the vertical lines are equally spaced. It indicates that the average distance between the air molecule is the same everywhere, and the average air pressure in three regions, that is A, B and C, is also the same. If the stem is kept steady and the prongs are stuck, the prongs are set into vibrations. It means that they are set into periodic motion in forward and backward direction. We will see step by step the result of such a motion. If during the vibration, the prongs of the tuning fork go away from each other, as shown in figure 15.2. The air outside the prongs is compressed and the pressure there increases. Such a state of high pressure is created in region A in the figure. The region in which air is at high pressure and high density is called compression. And the next step of vibration, the prongs of the fork come close to each other as in shown figure 15.2c. In this case, the air molecule near the prongs get more space to move away from each other. As a result, the air pressure in this region, that is region A, decreases. Such region in which air is at low pressure and low density is called rarefaction. However, students, the air molecule in this region, which were in compressed state earlier, transfer their energy to the air molecule in the next region, that is from A to B. So the air in that region goes to compressed state. Such a periodic motion of the prongs creates compression and rarefaction in air, and these are propagated away from the prongs. These are nothing but the sound waves. When these waves reach out ear, the eardrum vibrates. Accordingly, specific signals reach the brain and we get a sense of hearing a sound. Let us move towards what is propagation of sound and medium. We have learned, students, in the 6th standard that sound travels through some material, medium like solid, liquid or gas, and reaches us. But what if such medium does not exist between the source of sound and our ear? Sound generation and propagation needs medium like air. A simple experiment can do this. The experimental arrangement in this experiment, let us see what is that. A vacuum-tight bell jar is placed on a smooth horizontal surface. The bell jar is connected to a vacuum pump via a tube. We can remove air inside the bell jar using the vacuum pump. As shown in the figure, the bell jar contains an electric bell, which is connected to the power supply through the lid of the bell jar. At the start of experiment, the vacuum pump is off and the bell jar contains air. If the key to electric bell is now switched on, the bell starts ringing and the ringing can be heard from outside the bell jar. Now, if the vacuum pump is switched on, it starts removing the air from the bell jar. As the quantity of air inside the bell jar decreases, the level of ringing sound heard outside also decreases. If the pump is operated for sufficiently long time, that is long period, the quantity of air like inside the bell jar will be low. At this point, the level of ringing sound will also be very low. This experiment demonstrates that sound generation and propagation needs a medium. If the air inside the bell jar is totally removed, we will be able to hear the sound of ringing bell. Why? Comment your answers, students, in the comment section. Let us move towards frequency of sound waves. Using figure 15.2, we'll learn about how the vibration of tuning fork result in the generation of compression and rarefaction in air. Let us see that. See the cycle of compression and rarefaction in a sound wave and change in air pressure. One compression and one rarefaction together forms one cycle of the wave. The number of cycles formed in the air in 1 second will be decided by the number of the prongs of the tuning fork vibrates back and forth. That is, the number of vibrations of the tuning fork in 1 second. Number of such cycles that are produced in the air per second is called as the frequency of the sound wave. The frequency is measured in hertz. If one cycle is completed in 1 second, the frequency is said to be 1 Hz. For example, the tuning fork in figure 15.1 shows its frequency to be 512 Hz. It means that the fork vibrates 512 times per second. These vibrations will set 512 cycles of compression and rarefaction in the air per second. Thus, the sound generated by the fork will have a frequency of 512 Hz. The frequency of a tuning fork is decided by the dimension of the prongs, that is, length and thickness, and the material used for making the fork. Rest of the lesson we will see in the next video. Take care, students.